Good morning, mathematicians. We're back to it. I forgot to get things set up ahead of time, but that's okay. So I think last time started talking about poor Xed. We're back to it. Oh yeah, I did. I did manage to do a little bit of reading on the extensions, and I realized where I was going wrong. So I'll say something about that in a second. Yeah. Let's maybe get Reddit open. Maybe go to archive. It's proven time. Hell yeah. I gotta get a theme song or something. Well, I guess that's my catchphrase. Is I go like, "It's proven time," beep beep, and then like I transform into a costume and write some proofs. Yeah. Okay. Um. So let me correct my numerous mistakes, which I never make. How uncharacteristic of it. So at least in the case where, um, if we assume that A is abelian, so um, A is abelian, and we consider um, uh, G is some group and A as an G module. So A comes with some action. Then we would like to understand the classification of extensions of G by A. And in this scenario, it is the case that but okay, so there's an important thing. It's extensions um of G by A, but this is like with respect to A given this G module action. That's kind of the essential thing here. So then um, what was it? The first homology of G with coefficients in A. I believe that this is in bijection with the extensions of G by A, subject to this G action. So what that means is that the trivial class in here, the trivial class, does correspond to when E is the semi-direct product, where the action of this semi-direct product is given by the action of G on A. So that means in this setup, in this scenario, there's there is just one semi-direct product, but that's because we're it's important that we're viewing A as a G module here. Good morning, Will. Good morning, Will. And actually, I've got cohomology groups with me. So I was reading it last night, my bedtime reading, and uh, yeah, I figured maybe I'll just bring it with me here to make sure I don't say total nonsense. I might have already said something because both the first and second cohomology come up here. Yeah, see, I already lied to you. It's H2. This one is H2. This one is H2. H2 upper. Couldn't have got it more wrong. But that's the point. It's H2 upper. It's probably not worth me trying to explain it from the textbook right now. So, um, probably, probably I should make a video on this. I think that would be a good idea, like a proper pre-recorded video. The other thing too is that if you have this um, split extension, oh, what have I done? Yeah, so some of the weirdness comes between the difference between what split means in groups and what split usually means in modules. But um, part of it is that if you have this split extension, then H1 GA is records basically should be in bijection with the splittings. Good morning, Russ. Did you were you able to complete the rest of the question you had yesterday about groups and stuff? So yeah, so it's the I had a few things twisted around yesterday when I was talking about this, but it's the first cohomology that's in bijection with the splittings of some particular, where again here I mean the semi-direct product given to you by the action of G on A. Yeah, then H1A is in bijection with the splittings. H2 is in bijection with all of the extensions with respect to that particular G module action. Yeah. So that's what it is. You once encountered some interesting homotopy theoretic perspective on this extension stuff. Interesting. If you look at the two group of inner automorphisms or something like that. Ah, interesting. You mean it was a GRE question, so the answer basically solved it. Ah, I see. I see. Nice. Nice. Um, oh, I see. Right, because I guess the way you originally phrased it, right, was just which of these groups, which of these orders has only one isomorphism class, I guess. Yeah. You can think of semi-direct product as an A bundle over G. Aha. That makes sense. And A bundles are definitely expected to be classified by first cohomology. Isn't it is it first? I thought there's something there that's also second cohomology, right? Or what is it? There's a it's Rayburn. Weirdly, this functional analysis book has a great. I've mentioned this on stream before. Um, where do they talk about? Somewhere they talk about cohomology and oh yeah, sheaves cohomology and bundles. Somewhere in here. Uh, let's see. I remember this is the book where I first learned about such things. Okay. Um, first Chern class. Uh-huh. If theorem 4.2 dot 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 This bundle is determined by a class called the first Chern class of the line bundle, which is an H2 of Z. Right, let's go back. What's theorem 4 point? Oh, right. Yeah, so I remember there's something. Okay, this is the first cohomology group. I remember there being something, but there's also some isomorphism, right? Where the first, it's like first Czech cohomology ends up being isomorphic to a second cohomology. This is my vague recollection here. You're an undergrad student starting new on group theory and struggling. Any advice? Well, it's hard to give general advice, without knowing exactly where and how you're struggling. But um, there's maybe I would recommend. There's a book by Gallian, which is much more. I don't know what book you're using, but Gallian is a very probably one of the more down to earth and example heavy group theory books. So I would consider that. Um, Also, just like you need to hit yourself over the head with a ton of examples, um, most likely, in order to gain intuition for what's going on and to, see some pattern recognition. So, yeah, in the absence of more information, uh, it's hard to say more specific advice. You've taken algebra 1 and 2, and you think you know homology, but could I just give a quick explanation of the difference between cohomology and homology? Basically, it's just that the arrows go one way versus the arrows go the other way. I mean, technically, like really, it's just like, do your indices go up or down? Is like the main thing. Now, in yeah, exactly. As Nicholas said, yeah. Um, no, in practice though, what sometimes ends up happening is that when we have a cohomology, we end up taking the dual of some complex. So it's like if you had, I don't know, you had some complex like this, and then you took the dual, say with respect to some ring or something, now you would get a complex moving in the other direction. And so oftentimes in I put things in the wrong slots. Um, but oftentimes in nature, this will happen. But yeah. Learn every definition. Yes, that's true. You took it as directed study, and you regret not learning the definitions now. Yes, like I've said on stream before, in the hierarchy of things that you need to memorize, because again, math. Okay, yeah, the fun part isn't the memorization. Yeah, probably like me, you might have been interested in chemistry and biology, but in the earlier years when you need to do more memorization, you're turned off by this, and you're like, oh, I just want to like think about stuff. Um, but surprise, you need to memorize things in math as well, and in the hierarchy of things you need to memorize, definitions is number one. Because if you forget every other theorem, every other result from your class, then as long as you remember the definitions, you could still conceivably prove the thing that's being asked you in a quiz or something. But if you don't know the definition, you can't possibly offer a rigorous proof um, involving that object. So it's ultimately the most important thing. I mean, for like, you need to know what you're talking about, right? Like, imagine going into an English exam and you don't know what any of the words mean. Well, you're not going to do. You're just not going to do well. because you can't even like read the question, right? Um, so yeah, absolutely. Singular homology versus cohomology. Then there is more to it. Yes, that is true. Cohomology often tends to form a graded ring, and if you dualize it, you still get a binary operation on homology, but it won't quite be a ring. Yes, that's an interesting point. That that is an interesting point there. You only studied homology in the topological sense. I see. Are they the same thing? Yes. So, homology, right? So homology or cohomology, in general. Okay, I definitely need to make so many videos I need to make, but this has been coming up a lot lately, so I'm gonna make some like definitive video on it. But um, so you have some sequence, right? And I call this di minus one, whatever. You have some sequence, right? And okay, these could be vector spaces or abelian groups or modules. The fancy way to say it is it's a abelian category, but basically anything where you can take kernels and blah blah blah. And what is the so you have a sequence of objects, and the homology of that sequence, the nth homology group of that sequence is just defined to be the kernel of di modulo the image of di minus 1. And so this is very, very general, right? I've said nothing here about topology, right? I'm just saying you can talk about the world of homology anytime that you have a sequence of abelian groups or vector spaces or blah, blah, blah. And you can define this notion of this kernel by this image, and that is the totally like fully abstract definition of homology. Okay, there's other more complicated flavors and stuff, but this is a good swath of them. And so the homology that you know in the topological setting is just a very special case of this, right? Like the singular, like if you like, I'm guessing you did like singular homology, right? Well, what do? I mean, you build a sequence, right, where these are just particular maps into your topological space, right? And then the same thing with like simplicial homology and so on and so forth, right? So all of these topological forms of homology are just very special cases. And the general idea is, yeah, if you have some sort of class of objects, could be topological spaces or groups or whatever, um if you can the idea is you try to come up, okay, what are complexes, algebraic objects I can associate to this space, that encode some sort of information, and you build a complex out of it. um yeah. Yeah. You found that memorizing definitions just happens naturally with repeated use. Yes, this is true. I mean, just doing a bunch of exercises and proving things correctly. I mean, you inevitably just keep using a definition and you'll memorize it. Um, yeah, yeah. But I also still, I mean, I remember when the first course that ever kicked my butt was analysis, and I made flashcards and I wrote out the proofs of a theorem like 3 times in a row until it was like embedded in my head. Um, yeah. The point is not to memorize, but to recognize when they apply. Yeah, I mean, yes, yes. But if you don't know, if you don't know the definition, if you don't know the definition, then you're screwed. So you need to be able to know the definition, right? Um, you just joined. Did you really did PhD in math? Yes, I'm doing my PhD. I'm not quite done. I should be done soon. Might be done sooner if I didn't live stream every day, but here we are. Here we are, live streaming every day. Um, you are in last year of school, but on YouTube, you saw your school teacher said a PhD is worthless nowadays. That is incorrect. That doesn't make any sense. Yeah, also, your school teacher, I mean, does your school teacher have a PhD? Are they speaking from a level of authority on this subject matter? Because, um, yeah, that's just, I mean, let's I mean, what does it mean by worthless? Worthless for what? I mean, there's different PhDs and some, how are you looking at it, for example? If you're looking at purely in terms of a return on investment, well, for some fields, no, right? For some fields, uh, a PhD isn't going to make you a lot of money, but the reason a lot of people don't pursue a PhD is not because of money. It's because they're generally interested in the subject and just want to pursue knowledge. Um, but there are PhDs these days that will make you a lot of money, and there's certain fields that you simply cannot work in unless you have a PhD. So, um, your school teacher only has a master's in science. Well, I mean that's not nothing. They've got a taste of grad school, but yeah, I don't know. I take their opinion with a grain of salt. I don't know. Um, yeah. Simplicial was useful for intuition. You don't know why analysis is given before topology. Really? I mean, to me, it's quite clear why analysis is given. I mean, topology is just so much more abstract. Life is just so much better. Uh, I mean, analysis is the perfect thing to warm you up to topology, right? Because you're like, oh, I have this metric. Oh, certainly, I've got a metric in the real world or whatever. So certainly, life will behave the same. And then already, even in analysis with an arbitrary metric, you're like, wow, this is you already got some very surprising counterintuitive things. So I don't know. I think it makes perfect sense. Um, yeah, simplicial, singular, same philosophy. Quiz yourself on definitions, theorems, statements, and proofs in your intro to real analysis course. Excellent idea. Even better idea, quiz. I know it can bruise your ego, but find a friend in the class and quiz each other. What field is my PhD specialization? Local language, I guess I would say. That. They could be speaking strictly financially. That's true. Yeah, I mean, if you're speaking strictly financially, for the question about whether a PhD is worth it, um, probably no. But uh, even then, I don't know. It makes a big. It depends on what you're talking about. PhD in engineering, probably that's pretty good. PhD, you don't even need, master's degree in finance from a target school, pretty good return on investment, if you can hack it. So, um, yeah, I don't know. PhD in biology, well, maybe depending on where you go, where you work for. Um, I don't know. There are plenty of companies who exclusively hire PhDs. Yeah, that's also true. The metric space generalizations in topology are easier to understand if you've had analysis first. Totally agree. Random fun fact: the stable homotopy ring, for which we still know very little about, is the only known examples of a perfect ring. What? 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 Huh? That's impossible. Um, over which all left modules have projective covers. Wait, what? Wouldn't what about like a field or something? Am I crazy? There exists rings which are perfect on one side but not the other. Okay, semi-perfect ring. Definitions, examples. What do you left or right Artinian rings? Are known to be left and right perfect. Perfect meaning, oh, all flat modules are projective? Uh, you mean again? Isn't this shouldn't this be true for rings? Or sorry, for fields? Because everything's flat and projective for fields. Uh, am I crazy? But what is the stable homotopy ring? Let me see. Stable. Stable. Uh, well, where is it? Is it just ring spectrum? I'm lost. One more thing. After PhD, can you solve any math problem? Nope. Like in school, you struggle at basic calculus. Well, by the time you're done a PhD, you should be able to solve any basic calculus problem. In fact, by the time you're done a PhD, you might not be able to solve a basic calculus problem because somewhere in the middle, by the end of your undergrad, let's say you could solve a basic calculus problem, and then you stop using that or dealing with it. Actually, that's not true because you have to do a bunch of teaching during your PhD. So yeah, basic calculus becomes extremely easy. I mean, normally as a PhD student, you spend a lot of time grading calculus papers. So yeah, the things you struggle with now will be, like breathing air in the future if you keep working at it. Metric space is a part of Calc 2. Interesting. Interesting. Yeah. How did I choose to work in local Langlands? And how was the major choice made over a long period of time, or did you enter grad school knowing that's what you wanted to do? No, I didn't really have any idea. I had a vague idea. I was, the prof at my uh, the prof I connected with before my master's was just one of the few people around with algebraic geometry in his research description, and I was like, that sounds cool. And so I worked with him, and then I was like, well, I'll try and do similar sorts of things. And then I came here, and then my supervisor was like, hey, how does this project sound? I was like, yeah, okay, let's do it. That was basically how it happened. Fields are trivial examples of perfect rings. Okay, great. I'm not crazy. Stable homotopy ring is just the direct sum of all the stable homotopy groups. I see. And that's a ring? Interesting. PhD in engineering is fun. Yeah, it does seem fun. I teach a lot of engineers, and the it does seem fun when they like are building stuff like robots, and it's like that seems cool to be able to put the like fruits of your labor to see it before you and combine programming and building stuff. Seems like it feels powerful. Colleagues completing their PhDs while working at the company. Yeah, I mean that's the dream. That's the way to do it. Sorry, I had to put the phone down for a second. What did I say? PhD specialization was local language. Local language. Um, Specifically stable homotopy groups of spheres. Oh, maybe the keyword here is stable, and that gives you the ring structure. Um, Maps between spheres of arbitrary dimension, you can suspend them enough to make them composable. Interesting. Yeah, PhD is for the love of the subject. Yeah. You're going for math phys, which is not a great job outlook for some things. Yeah, arguably slightly better than math because uh, I think finance people, for example, if you need to bail the industry, um, prefer physics somewhat, just because even if you're theoretical, you still think more about how to actually apply these abstractions to the real world. Um, yeah, yeah. One thing I'd say though, Will, is I never thought I would ever think about anything other than math. And to be clear, about 90%, 98% of my day is just thinking about math. But um there is now, to my own surprise, after many, many years of thinking I would never feel um differently. I now, part of me is like, it'd be cool to go make money um outside of academia. Am I topper at my school time? I'm not sure what you're asking. If you're asking, am I like king shit of, my peers? No, I wouldn't say so. I would say there's definitely, I have a number of friends who I would consider smarter than me. But I also don't think I'm at the bottom of the people I know. So, which, like, statistically, that's what you should expect for yourself, right? I mean, assuming a normal distribution, you should probably assume that you're average. Um, there's some mathematical physics applications in there. Yeah. U of Toronto has some good AG people. Yeah, I mean, um, U of Toronto has good everything people. If you go look at their list of faculty, there's a lot of people there in a lot of subjects, and definitely some famous people. Um, yeah, yeah, I would say that. I mean, you could look at other universities too. You could look at other universities too. I'm trying to think. I mean, I'm not as familiar with the AG crowd. Like, there's some people at the University of Alberta. Um, but it also depends on like what you want to do. Um, yeah, there's definitely there's people in algebraic geometry scattered across the country. But I mean, of course, it's better to go where the concentration's highest. It's probably U of T, or maybe even uh, Montreal. Um, yeah. Just today happened. You happen to become a corporate sellout. Not actually, it's just a part-time job for a couple months to save up. Nice, nice. Linear algebra and Black-Scholes equation for financial economic analysis could make bank. Yeah, yeah. Uh, Abstractions rule. True. Applications are cool and all, but n dimensions is cooler. Yeah, yeah. I mean, hey, n dimensions are very applicable though, right? Because you can have like a very real world function that just depends on four more parameters, and now suddenly you're doing higher dimensional mathematics. Um, uh, and it's very practical. Or for example, one can model. This is my favorite example to give people about how higher dimensional mathematics is very practical. Um, if you imagine you want to model a gas, right, and so you have a whole bunch of particles. Well, what you could do is you could imagine, you could just sort of have a list of the position and momentum of the particles at each point in time and just sort of evolve that. But there's another perspective called the phase space perspective. And basically, what you can do is you can imagine that this entire configuration um, of particles is actually, so let's say there's n particles. You can imagine that this configuration corresponds to a single point in 6 times n dimensional space. So why is that? Because to encode the state of the gas, you want to know what you want to have for each particle. You want to know its position, x, y, z, let's say, and you want to know its momentum in each of these directions. But now you imagine that you have this for every single one of these particles. So you can imagine this huge coordinate vector, say in r to the 6n. And so now you've sort of compressed this whole entire state of particles in a gas in some box. You're treating this as a single point, and now the you can view the evolution of this state, say to some other slightly different state. As those particles are moving, you can imagine this as just being some sort of path that's being traced out in R6N. And this has practical applications because, taking this perspective allows us to do certain kinds of mathematics on the analysis of the behavior of gases and stuff. And so you can get particular theorems out of this. And so it's a very useful sort of analogy that allows you to, yeah, that is like a practical application of a very high dimensional space. Um, so yeah, yeah. Hope you found the analogous Simon's foundation. Yeah, yeah. How do you go about writing a paper? That's a big question. That's a big question. That's a big question. Well, and then we have another big question about explaining the Langlands program. Okay. Uh, range of sine x minus 1 to 1 inclusive. Hilbert spaces and their applications are very abstract. That's true. Yeah, Hilbert spaces abstract, but also super applied. Um, and speaking of, yeah, what is what is the general thing for a random variable in statistics? Well, it's a measurable function valued in a Hilbert space. Um, liquid functional analysis, I definitely haven't. One day I'd like to understand it. Okay, so we have two big questions here. How do you go about writing a math paper? Yeah, I don't think I know how to explain it. I mean, yeah, that's a good question. Maybe I should document my next paper or something. I mean, you have to have some idea. You have to have some theorem, right? There should be some main point to your paper. You should prove a theorem that has not been proven before, or you could also significantly shorten the proof of a theorem by introducing some new methodology or technique and demonstrate the power of that technique by significantly shortening um, known proof of the theorem. But in general, yeah, you need to have, and then well, it shouldn't just be any theorem, right? It needs to be a theorem that people care about, because anyone can prove a theorem, but to write a paper about it that people are going to want to publish, that's a different story. How do you go about actually writing it? yeah, I'm not sure I know how to explain such a thing. You just start writing. I don't know. I mean, there's lots of things to say about it, about how it's written and presented and um, whatnot. But um, yeah, I'm not sure. That's maybe a video idea as well. I gotta start tracking more of my video ideas. How to write a paper. Um, what writing a paper looks like. Maybe. Oh, I forgot there's a question I was supposed to talk about on stream today. We're almost at it. I'm not going to get to it. I need to get to work, but um, okay. Um, okay, how to write a paper and some stuff about cohomology. Okay. Um, okay, the Langlands program. Let me give you. So I don't know if you're still here, Neo, but I do have a couple videos on the Langlands Pro. I think I have like two videos that are like not called like a not entirely wrong introduction to Langlands program. Uh, but so actually, as an analyst, you'll really appreciate one part of this, um, and that is a central thing in study of the Langlands program are the L2 is the L2 space of some group. Um, and so, as you probably know, as an analyst, the L2 space this will break up into a discrete part and a continuous part, right? The discrete part of the spectrum and the continuous part of the spectrum. And well, I guess that's not so important, but very, very roughly, there's something called an automorphic representation, which is a representation of a certain group that lives in here. So to get slightly more specific, um, an automorphic representation, let's say of, I mean, this isn't quite, there's some technicalities, but well, an automorphic representation of GLNA should be an irreducible subrepresentation of we take this group and then we also mod out by a discrete subgroup. So that's what an automorphic representation is. And the Langlands program seeks to relate representations of this to representations of the Galois group, um, which are valued in, say, GLNC, for example. So n-dimensional representations of the Galois group. And so, in general, this is why people say that Langlands is a bridge connecting harmonic analysis to number theory, right? This Galois group encodes number theory. The L2 space, there's a whole bunch of analysis we can do in terms of these function spaces. And the reason that we care about this is basically we can go back and forth. So you can use results from number theory to prove analysis things and vice versa. So that's a super, super duper quick overview. Super duper quick overview. Quick test 2, medium range of consec inverse x. I'm not sure I know what consec means. Yeah, sorry. I'm not sure what consec means. But definitely I would love to talk more about we could talk more about the Langlands program. Step 1, know what you want to write down. Step 2, write it down. Yes, Arad. Yes, that's actually it. What is the significance of the new paper that Gates, Gorey, and Raskin of geometric Langlands and characteristic P? I don't know. I guess I should know because I claim to be someone who works in Langlands. Um, but this is it's sort of outside of my wheelhouse. What they're doing. Uh, why is it being weird? Yeah. Um, yeah, their stuff is a lot fancier than mine, I would say. Um, so my very super, I have not spent a lot of time looking at that paper yet, but um, if I understand correctly, they use results from characteristic zero to prove things in characteristic P, I believe. They're able to lift some results. So that's, I guess, pretty big. Um, uh, yeah, I guess that's a pretty big result. Um, uh, Certainly, it's a I don't know. Yeah, I don't understand it by any means. Um, but yeah, so I mean that would be cool because it's just a bridge between different versions of Langland's program. Gate scores Raskin is mostly show off how powerful their framework is. Yeah, that makes sense. Cosecant inverse cross range difficulty level medium. Well, I don't know about the difficulty level, but let's see, cosecant is what, 1 over sine. So its range should be everything, and its domain are not the everything but the multiples of pi. Um, yeah. Wait, no, 0 to 1. I guess it won't be everything. That's not true. Where is it? Yeah. Um, Anyways, that's why harmonic analysis topics were given in seminars throughout the year in your school. Maybe you should start attending that. You just have an aversion of analysis. Well, I don't know what to say. Analysis is based uh, because it's part of language. Don't take as disrespect. You're just trying. Like you still remember these ranges is very impressive. You just learned them. Gonna forget in 3 days. Well, don't forget in 3 days. Remember, remember. I mean, you can if you just remember if you just remember what sine, the ranges and stuff for sine and cos, then you should be able to deduce what the range and you should be able to deduce the range of all these other like secant, cosecant, and cot and tan, right? Because they're just various rational approximations to these. So um, actually, the image of sine is all of C. True, we should be viewing these as complex functions. Um, Absolutely correct, Arad. You were trying to prove that if F is Lipschitz, uh, where H is the S-dimensional Hausdorff measure, and A is just a set. Um, well, I was just about to log off. I'm not so sure I would be able to help you um, if I wasn't about to log off, anyways, Antonio. But maybe ask again tomorrow and we can take a look at this Lipschitz stuff. Sarah in an interview said if you learn something correctly, you won't forget it. Yeah, I guess. But also, Sarah is Sarah. You know, I was listening. Okay, gonna go on a slight rant. I'm trying to leave, but I'm gonna go on a slight rant. I was listening yesterday about it was a sports science podcast, and there's this guy who's like a trainer and sports scientist, and he was talking about the fact how he was talking about there was some famous guy who like he was talking, he was debating about, the efficacy of like the major five lifts, in particular squats, and he was talking about how there's this one guy who, like, yes, generally speaking, those are all great exercises, but also the exercise, it somehow depends on your build, right? So he was saying, for example, some people with, like, if you have very long arms, for example, like, certain exercises like the bench are just not going to be your exercise. Like, you're gonna do best at bench, or it's gonna, like, hit your pecs the most if you happen to have short arms, right? And so it's not necessarily one size fits all thing. And so he was talking about, there was like this very famous bodybuilder, powerlifter, whatever, who, squatted some insane stuff, and he was like, oh, he was like, well, and people are like, oh, how do you get so swole? And he's like, well, you got to hit the squats. Squats is, you got to hit squats. Um, but that's because it worked for him, right? It was for his body type. He got the most stimulus out of squatting, and you could say maybe for a lot of people that's the most stimulus, but it's not necessarily generally true. So, anyways, the point is, if Sarah is like, "Oh, you just got to learn things correctly," I'm like, yeah, maybe, but I don't know. If you're like me, you got to, like, read it 500 times. I don't know, or write it out 500 times. Okay, I really gotta go. Sometimes you notice you learn, when you learn anything very much, the ego is grown, but it's just fake. Yeah. What do you think after PhD? Um, uh, yeah, I don't know. It's I don't know. It would maybe be different. Ego. I mean, this is a big question too. But ego is, I don't know. Maybe I'd have a much bigger ego if I was at, like, a top five worldwide school. But so definitely, I'm sure some people come out of grad school with much bigger egos. But also, math is a humbling thing, right? There's no hiding or posturing. Beyond a certain point, it's like, you can't fake it anymore. Like, when you're an undergrad, you just throw around a bunch of big words, and the other undergrads think you're smart because you said the word cohomology a bunch of times. Um, yeah, it becomes clear who knows what they're talking about and who doesn't. Uh, the part I can't figure out is, if A is contained in the union of some EI, how is FA in the union of FEI? Wait, what's EI? What are the EIs? Okay, maybe Antonio, if you can give me a precise reference from the proof that you're looking at tomorrow, maybe we'll go look at that. Tom Platz, right? That was the guy. Yeah. I interviewed Buzzard. His advisor, Richard Taylor, told him to try and understand the hardest problem or theorem in a subject and then backtrack. Maybe, allegedly that's what Schulze did, and now he's like the most giga chad mathematician. Okay, I'm leaving for real now. Go prove some things. Go read the hardest thing and work backwards. And I'll see you then.